Welcome here. Today's episode is brought to you by the letter Q, which of course stands for charge. And this is day 32. I screwed up the count badly last week, but regardless, even though I can't keep track of days, I'm still going to see if I can teach you a little bit of physics. And what we're going to do today is we're going to look at a few different topics. Each one is going to be pretty short and not very mathematical. And there's not going to be much of an assignment at the end. And what you're looking at right now is, of course, a Van de Graaff generator. It's what Albert used to style his hair a little while ago. And the reason why today's episode is brought to you by the letter Q is because Van de Graaff generators, they are great at building up a huge charge. And we'll give you a little tour of this thing and show you exactly how it builds up such a big charge. Okay, now you'll notice that over here we have your basic cord, so it plugs into the wall, and in the bottom of the unit there is a transformer which basically boosts the wall voltage from 120 volts up to, it could even be several 100,000 volts. Okay, so you've got in that lower unit a huge potential difference, a huge charge imbalance. And that charge imbalance, what it does is it causes electrons to jump on to the rubber belt here, and when you turn the machine on, this rubber belt is rotating, it is turning, it is going up one side and down the other, okay, up one side and down the other. Okay. And at the top of the unit, if you remove the top, let's take a look inside. You can see the rubber belt right there, and when the charges which are traveling on the rubber belt, when they get to this metal screen, they jump off on the metal screen, and from the metal screen they go down these pieces of copper wire, and the charges, okay, they spread out along the big metal sphere right on top. So yeah, the Van de Graaff, it manages to develop a huge charge on this big metal sphere right on top. And in just a bit, we're gonna use the Van de Graaff to demonstrate exactly the difference between voltage or potential difference and current. All right, let's see how this Van de Graaff works. We're gonna turn it on. Notice the location is a little different because it's darker here. You can see the sparks better. And I'm going to put my hand pretty close to it, and we'll see what kind of sparks it gives off. Okay, some pretty good ones. Let's try it with a knife. Now you figure it's a conductor, it's got a pointy end. This should give a super big spark. Let's see what happens. Hardly anything at all. If you look close, just as the knife comes close, maybe you can see a tiny little continuous spark. Okay, let's shut this thing off. And explain what was going on there. Now you'll notice when I shut it off, it's still got a load of charge on it. And yeah, it gives off one final spark before it's completely neutralized. So you can see I've suffered no ill effects from the Van de Graaff, although that might be a subjective thing. But what was going on there was the Van de Graaff, it was generating a potential difference of several 100,000 volts. The potential breakdown of air is 30,000 volts per centimeter. In other words, to produce a spark 1 centimeter long takes a potential difference, a charge imbalance equivalent to 30,000 volts. And I was producing sparks that were, I don't know, say 5 centimeters long. So 5 centimeters times 30,000 a centimeter, that comes out to 150,000 volts. The potential difference between me and the Van de Graaff generator was 150,000 volts. There was a huge charge imbalance between the Van de Graaff generator and myself. And that charge imbalance, that huge concentration of charge on the Van de Graaff, was able to propel electrons from here through the air right into me. Now the question is, how come I suffered no ill effects? Like 150,000 volts is a lot of volts. Well, you got to remember, the voltage was huge. Big charge imbalance propelling those electrons from the Van de Graaff generator into my hand. But not very many electrons were actually being propelled. Okay, so we had a big voltage, okay, causing those electrons to jump that great big gap, but not a lot of electrons were actually jumping the gap. So we had a big voltage, but a very, very small current. Okay, thus, no humans suffered any cruelty at the expense of this demonstration. For injury to occur, you got to have a big enough voltage and a big enough current. Here we have the big voltage, but no current. So there's a good illustration of the difference between voltage, basically the electromotive force, the charge imbalance that's pushing the electrons, and the current. Okay, how many electrons are actually flowing? In just a bit, we will take a look, as I said, at a few more little things. Let's take a look at negative potential. Not the most important thing in the world, but occasionally you'll run into people talking about something with a negative potential, and you might see a multiple choice question or two on your test with regards to this. So let's talk about our Van de Graaff generator. Here it is. The upper orb has a huge positive charge on it, and of course, if this were the case, it would be attracting electrons off my hand towards it and making the spark that way. But if this were the case, we might say the potential of the Van de Graaff is 150,000 volts. In other words, the potential difference between the ground and the Van de Graaff is 150,000 volts. Remember what 150,000 volts means. 150,000 volts means 150,000 joules per coulomb. So if you had positive 1 coulomb of charge on the ground, you know, down there, and it's going to go up through my body because my finger is getting pretty close to the Van de Graaff. If that 1 coulomb of charge is going to go from the ground to the Van de Graaff, remember, you're going to have to do work on it. The charge does not want to go in that direction. It's positive, and these positives are repelling it away. So to get the charge from here to here, you're going to have to take the charge and do work on it. 1 coulomb of charge, you're going to have to do 150,000 joules worth of work on it. Okay, now here's another situation. Here's our Van de Graaff, and this time our Van de Graaff is loaded with negative charge. Now in this situation, if I had my hand close by, well, of course the Van de Graaff, it would be repelling electrons onto my hand, like so, and that's the way the sparks would get formed there. Now in this situation, we might say the Van de Graaff is at a potential of negative 150,000 volts. So what exactly does that mean? Well, remember, negative 150,000 volts means negative 150,000 joules per coulomb. If you had a positive 1 coulomb charge on the ground here, and you wanted to get it, and you wanted to get it up to the negatively charged Van de Graaff, you would have to do, well, negative 150,000 joules worth of work. What exactly does the negative mean? Okay. Well, up here the work was positive, and you had to do the work. You had to physically drag it because the charge didn't want to go that way. Well, here, the charge is positive. We got a bunch of negatives here. The charge is going to be attracted towards it. So really, you don't have to do any work. You can just sit there and watch the charge move from here to here on its own. In other words, the electric field is doing the work. That negative sign means the electric field is doing the work. We'll come right back and we'll take a look at another short little snapper of a topic. Sorry, maybe I spoke too soon. Here's a question that is actually still related to what we were talking about with regards to negative potential. Here are a pair of charge plates, A and B. This one has a charge of -3 coulombs, and this one, it has a charge of -1 coulomb. And the question is, which is at a higher potential? Well, remember, to move a positive charge to a higher potential, you have to do work on it. You have to take that charge and physically drag it along. It does not want to go there on its own. So which of these things is at a higher potential? And remember, to move it to a higher potential, we got to actually physically drag the charge along. We're going to have to physically drag a positive charge along, and it's not going to want to go on its own. So suppose we have a positive charge somewhere in there. Okay, so these negatives are attracting it with a little bit of force, because there's only a couple of them. These negatives are attracting it with quite a lot of force. So on its own, the charge, it wants to go this way. Okay? So if you drag the charge in this direction, you're going to have to do work on it. You're going to have to physically drag it from here to here. So that means plate B is at the higher potential. Because remember, to move a positive charge to a higher potential, you have to physically do work on it. And okay, I think that is definitely it for negative potential. We'll take a look at something else in just a sec. Here is something that I know you're just dying to know about: electron volts. Electron volts are actually a labor-saving device. So here's a typical calculation that you might have to do. Proton is accelerated through 100 volts. How much kinetic energy does it gain? Okay, I'm pretty sure you can probably do that one. 100 volts of potential difference. The best way to visualize that is with our favorite piece of electrical apparatus, a pair of oppositely charged plates. So here we go. There's our oppositely charged plates. There's 100 volts of potential difference between them. And we're accelerating an electron through this 100 volts of potential difference. So the electron is going to start here. And yeah, let's face it, if we're grabbing onto the electron here, these positives are going to push it that way, these negatives are going to pull it that way, and yeah, this electron is going to go from this side all the way to the other side. Now it starts at rest here, let's say, and when it gets to here, it's moving. The question is, how much kinetic energy does it gain? Okay. So remember, the increase in kinetic energy, well, that's the same as the work done on this thing. What's the increase in kinetic energy of this proton? Well, it has no kinetic energy here, so however much kinetic energy it winds up with over here, that's its increase. What's the work done on it? Well, that's equal to the charge times the voltage you move it through. What's the charge? Well, most people are going to say, well, that's 100 volts. That's equivalent to 100 joules per coulomb. So that means our charge has to be in coulombs. 1.6 times 10 to the minus 19. That's what proton or an elementary charge is. You multiply by your potential difference, which is 100 or 10 squared. Okay. Add the exponents and you get 1.6 times 10 to the minus 17 joules. No problem. Okay. But there is an easier way. Okay. And that's where electron volts come in. Electron volts, as I say, they are used by high-level physicists mostly to save themselves some work. As a rule, high-level physicists, they are actually surprisingly lazy. So here we go. How can we do this question and save ourselves a little bit of work using electron volts? So the reasoning would start out exactly the same, okay? So the increase in kinetic energy, which is basically however much kinetic energy you wind up with over here, that's the kinetic energy you gain, that's going to be equal to the work done, which is the charge times the voltage. And a high-level physicist, they might say, well, what's the charge here? Well, it's a proton. It is 1 elementary charge. What's the voltage? Well, it is 100 volts. 1 times 100, easy. That's going to be 100. What are the units going to be though? We can't say that the units are going to be joules, because even though this was in joules per coulomb, this wasn't in coulombs. Okay? So what are the units going to be? Well, remember, units always follow from the way you calculate something. This charge is in elementary charges, and this potential difference is in volts. So there's your answer, 100 elementary charge volts. But that sounds kind of weird, and it's also kind of hard to write. So what physicists do is they will say, well, an elementary charge is the charge on an electron, as far as absolute value is concerned anyway. So what are our units here? Well, here we have an elementary charge, which is the charge on an electron. Here we have a bunch of volts. So there's your units, 100 electron volts. Okay. So an electron volt, abbreviated EV, remember, it is a unit of energy. It is a unit of energy. It's a very small unit of energy, much smaller than a joule. It is basically, the definition of it would be the energy needed to move 1 elementary charge through 1 volt of potential difference. Okay, now let's try one quick question here, or you can try one quick question. To kind of cement your understanding with regards to this. Okay? Here's the question. How many coulombs is 1 electron volt equivalent? All right, so here's the question we want to look at. To be perfectly honest, I screwed it up before. I think I said how many coulombs is 1 electron volt equivalent to. My bad, that is complete garbage, because an electron volt is a unit of energy, a coulomb is a unit of charge. So that is a bad question. What I should have said was 1 electron volt, well, how many joules is it equivalent to? Okay, 1 electron volt, how many joules is it equivalent to? All right, let's see if we can do this. Okay, now remember what an electron volt is. Okay, it's the energy or the work needed to move 1 elementary charge or a proton through 1 volt of potential difference. Okay, so if you want to figure out the work needed to do that, or the energy needed to do that, well, you go W is equal to the charge times the voltage. And remember, if you want this answer to come out in joules, well, this, remember, is in joules per coulomb. This has to be in coulombs. Okay, so here we go. 1 elementary charge, that is 1.6 times 10 to the minus 19 coulombs. and then we're multiplying by 1 volt, which is 1 joule per coulomb. And yeah, the coulombs cancel, and you're left with 1.6 times 10 to the minus 19 joules. So as you can see, an electron volt is equal to a very small fraction of a joule. It is equal to 1.6 times 10 to the minus 19 joules. And what I was talking about just a little while ago, I think I said electron volt is a very small fraction of a coulomb. That is complete garbage. An electron volt, remember, is a unit of energy, so it's going to be a small fraction of a joule. All right, one more short topic to go. The last thing we want to take a look at today, potential due to a point charge. So here's a point charge Q, and suppose there's some distance d, or some people like to refer to the distance as r, but you're some distance from it. Well, what is your potential equal to over here? What's your potential difference between this point and this point? We've been calculating potential difference using E.P.E, right? E.P.E tells us all we want to know about the potential difference due to an electric field. But in this situation, V is not equal to E.P.E, okay? In this situation, if you're talking about the potential difference because of a point charge, you cannot use V equals E.P.E. Remember, V equals E.P.E is good if the electric field is constant, like if you're in between a pair of charged plates. But in this situation, you're talking about the electric field due to a point charge, and you're right to remember that the electric field due to a point charge is calculated like this, KQ over R squared. In other words, the electric field changes as the distance, D or R, or whatever you want to call it, changes. So because the electric field is changing, if you're talking about a point charge, the potential difference cannot be calculated using E.P.E. You have to use another formula. What that formula is, we are not going to worry about it. I just want you to realize that in this situation, E.P.E is not applicable because the electric field is changing. Take a look at this down here. This is kind of related to what we're talking about. It gets you thinking a little bit. So here's a point charge Q, and it's positive. And here's one positive charge, some distance D1 from Q. Here's another positive charge, okay? And it's some distance D2 from Q. Now, which of these potentials is bigger? Okay, is this charge or this charge at a bigger level of potential? Okay, how can we figure that out? Well, think of a gravitational field. Right now, the orange that's higher, it has more potential energy, right? Because when I drop it, well, it falls further. So it's kind of simplistic, but you can apply the same kind of thinking to this. Okay? If you got a hold of both these charges and you let them both go, which is going to move further? Well, they're both going to be repelled because they're both positive and this is positive. They're both going to be repelled in this direction. And you can see, obviously, that no matter where they end up, well, this one is going to move a little further. So we would say that V1 is bigger. Okay? The potential there is bigger than the potential there. And that is good enough for today. The best part of today is that there is no assignment associated with this. Just make sure you understand everything. And tomorrow, we're going to start taking a look at magnetism. Remember, this unit is all about electric and magnetic fields. So we are done with the electric fields part. Tomorrow, we will start with the magnetic fields part. We'll start off with mostly a review of what we did last year. See you then.